So for today's speakers, I'm pleased to present you 3 speakers. Unfortunately, we were supposed to have 4 speakers, but one speaker was not able to attend today. So our first speaker of today will be Romain Deleu. He's a PhD researcher in hydrogeology at the University of Namur, which is in the south of Belgium. And he will immediately take us underground because he will give a presentation about the hydrodynamics in karstic environments with the use of multi-point tracer tests. Our second speaker of the day will be Matan Ben Asher. He's a postdoctoral researcher at CNRS at the laboratory of EDYTEM, which is at the University of Savoie Mont-Blanc, which is, of course, in the south of France. He will talk to us about dye tracing of snowmelt in mountain permafrost. And our last speaker of the day will be Amaël Poulain, hydrogeologist at TRAQUA, and of course my colleague. And he will tell us more about dye tracing to characterize artificial water networks. So I will stop sharing, and Romain, you can prepare your presentation.
Yes. Let me share my screen. Is it okay like this? Can you see my screen, Sophie?
Yes, we can see your screen.
Perfect. Okay, good morning, everyone. So I hope we are all awake for this first session. My presentation will be about research I did during my PhD thesis, which is still ongoing. The title will be Multipoint Dye Tracing in Karstic Rivers, Early Results from Transversal Configuration. So first of all, what is a multipoint dye tracing? Well, this is a tracer test in which we use multiple fluorometers at one location. So for example, you can place one on the left side of the river and one on the right side of the river. This is what we call multipoint dye tracing. And the transversal configuration is where we use multiple fluorometers which we place along one transversal cross-section of the river. So as I said, one on the left, one in the middle, one on the right, and you can place as many as you want as long as you have them. This presentation is based on an article that was published last year. First of all, let me do some quick reminder. I guess probably most of you know all of this, but just some theoretical notions to make sure that we understand each other. There are multiple processes associated with solute transport in rivers. The first one, the main obvious one, is advection. So basically it means that the solute is transported along with the flow of the fluid. So in a conduit in which it is very linear, there is only not so much turbulence, not so much obstacles, then you can have mainly advection. This is the case, for example, on the picture. We can see a river that is flowing very calmly. This is mainly advection. In rivers where you have only advection, or mostly advection, you can have a signal, a breakthrough curve that took very narrow and very high concentration. So this is due to advection. If you add to that dispersion, that's mainly longitudinal dispersion, you can have a curve that become more smaller and spread out through time. This is due to obstacles and turbulences in the river, like in the picture, that makes the tracer more spread out through time, so the curve is longer. And then if you have one last process, which is called retardation effect, you can then have a curve that becomes asymmetrical. So your curve is not symmetrical at the peak. This is because some tracer can get stuck on side pools and slow zones like this on the diagram. And this tracer is then released later in the main stream. This makes the curve asymmetrical like this. The tail of the curve is longer. So these are the three processes, main processes affecting the solute transport in river. There are other, but I only talk about this one. So for this research, well, you probably know that tracer tests are very helpful to characterize a karst system. You will have a lot of examples in this webinar. And we also know from previous studies that lateral heterogeneities can be significant. That means that the signal on the left side of the river can be different from the right side of the stream. So the question we ask ourselves is, does the lateral position of the fluorometer affect the tracer signal? And the answer is yes, but how and how much? We will try to answer that in this presentation. So before we start, here is a graph that is a bit old, but very nice. You have an injection on the left side of the picture, and you have the breakthrough curve depending on the left side or the right side of the stream and the distance. And you can see that, of course, for very short distance, the breakthrough curve is very high and very narrow because longitudinal dispersion is not yet very intense. But as you get further, the curve becomes more flat and spread out because dispersion is cumulative with the distance. And on this graph, you can see that the signal in the center on the left side and in the right side are in fact very different. So already a few decades back, this subject was known. We know that there was differences. So we will do this. We have a karstic river. We will place a fluorometer on the left side, on the right side, in the middle, and see the differences. So for the on-site measurements, first of all, we chose the Boron cave, which is in Wallonia. And in this cave, there is a river flowing from the left to the right on the map. You can see it's in blue here. And you can see on this map, we did two cross-sections. Cross-section 1, which is closer to the injection point, and cross-section 2, which is further away from the tracer injection. For both cross-sections, we have a control. This is one fluorometer placed 10-20 meters upstream the cross-section. And for the cross-section, well, we place multiple fluorometers along this cross-section. This looks like this on the field. You have a rope going from the left side to the right side. You have multiple ropes suspended vertically from the main rope. And on those ropes, we attach fluorometers. The fluorometers TRAQUA provided. Then we measure, of course, the velocity of the flow. This is helpful to determine the flow rate. All the black points you see on the graphs are the point where we measure the velocity. And then the colors are the interpolation. So we have a velocity kind of map of the cross-section. This is helpful to know what is going on in the hydrodynamic of the cross-section. You see for the cross-section 1, we are going from minus 0.05 meters per second to almost 0.25 meters per second. Minus is, of course, current that is backward. So the current is going upstream. So you can see the velocity for the cross-section 1 is not so high, and we have some zones of negative velocity. For cross-section 2, we have the same colors, but this time it's going from minus velocity to more than 0.7 meters per second. So it's much higher. So we probably have a very much more advective flow on the cross-section 2 with much more turbulence. And you can see on the profiles, you can see the fluorometers. We have 8, 11, 12, 13, 14, 15. Those are fluorometers we placed on the cross sections. Then we inject 20 grams of uranide at the injection point. This looks like this. And then we see what the breakthrough curves are for each fluorometers. Here you can have a video of the tracer cloud passing by cross-section 1. I hope it will work on your screen. So you can see it's becoming quite green, and then the tracer is passing by, and after about an hour, it's completely gone. So let's see what it gives us on the breakthrough curves. This is the result for cross-section 1. So you have, first of all, the breakthrough curve in gray is the control fluorometer, which was a bit upstream. I will tell you later what it is used for. And then you have 8, 11, 12, 13, 14, 15, which are the fluorometers placed along the cross-section 1. You can see that the signal is quite different. We have 8, 11, 12, 13 that are very similar. And then we have 14 and 15, which are a bit strange. They are not behaving the same way. We will talk a bit more about that, but what you probably already guessed is that 14 and 15 are located in zones of negative velocity. So of course, this has an impact on the breakthrough curves. For cross-section 2, this is not so heterogeneous. We have much more similar breakthrough curves. There are some differences. For example, number 8 has globally lower intensity than, for example, the 11. We have, in terms of recovery rate, 8 has not enough recovery rate compared to the others. So there are some differences, but not so much. It's very similar. And it's probably linked to the fact that the velocity is much higher. And also, mostly longitudinal dispersion has helped to make the signal more spread out through time, making the heterogeneity less visible. I did some CFD simulation. So CFD is a computational fluid dynamics, which is a way to simulate a flow of a fluid, any kind of fluid. In that case, I will use water, of course. The model, well, I'm not going too much into the detail, but I use the PISO algorithm. It's an algorithm which is implemented in the software OpenFOAM, which is an open software. The model is 3D. It's working with the finite volume. It is transient, and there is only one incompressible phase, which is water. Then I simulate the flow and the solute transport. There is advection, dispersion, and diffusion being taken, and this simulation is done for 60 minutes. There is an automatic time step adjustment to allow for stability, so that the courant number is below 1. So of you who know all this know that it's really important to stay below 1, because otherwise the model becomes unstable. And I did a mesh of the cross-section 1. You can see it on the right side of the screen. I developed it in Blender, which is a model software that is helpful to draw things in three dimensions. And of course, I used bathymetric data to draw this. So we measured the depth of the river at many locations. And this allowed me to draw this 3D model. And of course, this model can give simulated breakthrough curves at the location of fluorometers. On the lower part of the screen, you have the boundary conditions. There is only one that I want to point out, is this one for the scalar, for the inlet boundary. The scalar is for the concentration of uranine. So of course, for the inlet boundary, which is here, I used the control fluorometer. So I used the breakthrough curves of the control fluorometer to make the model simulate an arrival, a progressive arrival of tracer at the inlet boundary. So this allowed to have a simulation of the tracer cloud reaching the cross-section 1, which is 15 meters downstream the inlet boundary. This is a video of the result. I see it work. So you have the time from the injection, and after 10 minutes, you see the cloud arriving. And then you can see how it's spreading out through the mesh. You have many phenomena. You have turbulences. You have negative velocities. You have some tracer stuck on the sides. All of this is helpful to visualize the hydrodynamic of the river and maybe explain the differences we have on the breakthrough curves. So the results of the breakthrough curves simulated from the CFD look like this. You have 8, 11, 12, 13, which are very similar. And then nicely, 14 and 15 are quite different. So this is very similar to the field result. The only difference is that we have a lot of strange signal for 14 and 15. If we average this out, this gives us the dashed lines. You have the black dashed line is the simulated breakthrough curve for the position 8, 11, 12, and 13. This is an average concentration for all those 4 fluorometers. And then you have 14 in green and 15 in red. You have the measured curve in plain colors and then the simulated value in dashed. So you can see that all of this is quite similar. We have a strong correlation between the simulation and the measured breakthrough curves. And to come back before, I forgot to mention, on the top of the screen is a cross-section showing the concentration at one point of the simulation, showing the difference in signal across the section. So you can see that on the left side of the section, we have high concentration, and on the right side, we have low concentration for fluorometer 14 and 15. So this is valuable for the peak of the first fluorometer here. At this point, we can see that there is a lot of difference in concentration of tracer. In terms of its interpretations, well, for cross-section 1, it is very clear that fluorometers 14 and 15 are affected by a hydrodynamical phenomena, which makes the breakthrough curves of these fluorometers different. This is linked to an eddy current, a strong eddy current on the side of the river, because there are two obstacles, one upstream and one downstream at this location, and this makes the side of the river there much slower, and you have a recirculation of water in this area. This is why we have negative velocities on the profile at these locations. This eddy current is clearly visible on the breakthrough curve because it makes the curve quite different than on the other side of the river, which is more advective. So this is quite interesting because we can see that at this distance from the injection point, even the slightest hydrodynamical phenomena can have a strong impact on the breakthrough curves. And this is also visible on the model. This is the CFD model showing the streamlines. So you have a simulation of particles being transported with the flow, and you can see that some particles are quite stuck in the zone of fluorometer 14 and 15 there. You can see the circles, the circular motions. This is the eddy current. The section 1 look like this. And for cross-section 2, we have, in fact, the stream is splitting in two at the cross-section 2. We have fluorometers 11, 12, and 13 that are characteristic of the left stream, and then 14 and 15 that are characteristic of the right stream. And if you look closely, this is not very clear, but this is the best I could observe from this breakthrough curve, is that 14 and 15 are delayed. You can see that the peak is 3 minutes late compared to the other flowmeters. And I think this is probably linked to the fact that the split is done upstream and the signal on the right side is slower than on the left side. And we can see that on the velocity profile, we could see that the velocity was higher from this right stream than for the left stream. And then finally, we have the flowmeter 8, which was placed on the side of the river, which has a too low recovery rate. This is because he was really stuck on the side where the water was very slow. And this section looked like this. Maybe I can go back on the velocity profile to show you the split. Yes. So you have the left stream here on 11, 12, and 13, and then the right stream on 14 and 15. And you can see between the two, there is a slow and even reversed flow between the two streams. So, and you can see that the velocity on the left stream is much higher. It goes up to 0.7 compared to the right stream, which goes only up to 0.2, 0.3. So this can explain the slight delay in the peak. So of course, this is a very small heterogeneity. You must look really in detail to see this. But this is clearly showing that, yeah, for the conclusion, this is perfect. This is clearly showing that the heterogeneities can be correlated with the velocity profile. An eddy current can have a significant impact on the breakthrough curves, as you have seen for cross-section 1. The CFD model is well correlated with the on-site results, and it gives a visual explanation of the heterogeneities. And finally, the breakthrough curves in the advective stream can be significantly different from slow or reverse flow zones. Of course, all of this study is for a small scale. This is why it was clearly mentioned in the article, because it is only for small scale. So what happens if this is for a much bigger scale, much bigger river, higher distance? Of course, this will be completely different probably. So that's why we want to repeat the experiment in a much larger scale. For the perspective, yeah, repeat the experiment in other sites of larger scale and study the spread of stresses through a large body of water, like an underground lake or something like that. Thank you for your attention. If you have any questions, do not hesitate.
Thank you very much, Romain. So yeah, if you have questions, you can either ask them in the Q&A box on the top of your screen, or by raising your hand in the reactions button, also on top of your screen. Don't hesitate. Or of course, you can also ask questions directly via email, Romain, I guess. Yes.
No problem.
So
the article is available online. It's really easy to find. It's open access. So if you are interested, you can just have a look.
okay. There seem to be, let's see the Q&A. There's no questions. No, they don't. There's one question from Matan. I don't know if you have seen it. How did you measure the velocity?
The velocity is measured with a device we have at our department. This is a device that helps us to measure the flow rate thanks to the velocity. It is a probe that is using the Doppler effect. I can give some more detail, but I don't have them right now. But this is very easy probe that can be easily found everywhere online. This is using the Doppler effect of the current. So you just have a vertical metal bar, on which the probe is attached, and then you place it at different depths for different verticals, and then you interpolate all that, and you get the flow rate of the river.
Another question from Elke. Why don't you measure the flow with the salt dilution method?
Well, we could do that, but because we have this probe that help us to have the velocity very easily in just less than an hour, you can have the velocity profile of a cross section. I think this is really nicely done, and on the field it's perfect to use that velocity measurement. Of course, maybe it's if we have less access or something, maybe it could be more easy, but yeah, the velocity measurements are quite easily done.
Reaction from Elke, she said it's much more accurate under these conditions with the salt dilution method. Okay,
maybe we can have a look on that. Yeah, I think our way of measuring the velocity is already accurate, but maybe salt dilution will be accurate also. It's possible.
Okay, thank you. I think, are there any more questions? No, they don't seem to be. I have a little, of course, I'm not an expert at all in hydrogeology, but I do have a question. Did you choose the cross sections because there was eddy currents and a split river, or was it more random chosen?
Well, we wanted to have an heterogeneity of our profile, so we chose a cross section that was located in a place where the flow where the cross section was not completely let's say linear, but we tried to remain reasonable, not to place the fluorometer, for example, in a zone where it's completely dead or anything like that, because we want to see the impact of an heterogeneity. So we chose a section that maybe has some hydrodynamical phenomena, but also by being reasonable. So a bit of both.
Okay, well, thank you very much, Romain.
No problem.
I think you can go to the next speaker, Matan, if you can share your presentation.
Yes. Okay, can you see it?
Yes, we can see your presentation.
Okay, thanks. So thank you very much for organizing this interesting webinar. I will take you high up into the mountains. And first, I would like to say that unlike the previous presentation, what I'm showing is a very it's an ongoing research, and it's actually started quite recently. So I will not have so many results to show. I will be more focusing on how we use dye tracing, and I think it's a bit of an unusual settings. And the second thing to point out is that I am not a hydrologist. I'm a geomorphologist. I'd be really happy to take any tips or any knowledge I can take from this webinar from if there are any experts in the crowd. And okay, so I belong to a group in the University of Savoie Mont-Blanc that we work on mountain permafrost. So maybe a few words about mountain permafrost. So most people are familiar with permafrost, with the Arctic permafrost, which are what, by definition, permafrost is just ground that is permanently frozen. It has no seasonal thawing. It's always below zero. So it means that any processes related to water are not really happening because the water are frozen. So so unlike Arctic permafrost, which is, I think, a bit more familiar, people are more familiar with, which is frozen soils in the Arctics. Then we hear about them with they thaw, and there is carbon dioxide that is being released, and woolly mammoths that are being found. So in the mountain permafrost, it's usually frozen. It's more rock that is permanently below zero, and it's just cold because it's high. And in the Western Alps, where I work, we usually find mountain permafrost roughly above elevation of 3,000 meters. And again, we know things are warming, and we see the permafrost thawing also in the mountains, and we know we see also increase in destabilization and increase in rock falls, and that's why we are very interested in studying it. And specifically, we are interested in my group is about water. What happens to water in the mountains, in the fractures, in how does it influence the stability of the permafrost and the rock wall. This is in this slide. It's an example of a rockfall scar. Okay, it's a famous pillar close to the Mont Blanc Massif, and there was a big rockfall. And just this photo was taken a week after the rockfall, and you can see that on the scar there's layered ice that accumulated, and there's water running along what used to be the fracture surface. So we know water are influencing the stability of the rock walls. And it can be, there are many ways it can happen. It can exert hydrostatic stress. It can lower friction. It can thaw ice that held maybe some of the rock. It can also advect heat and have a positive feedback on the thawing of the permafrost and destabilization of the rock. So obviously water play a key role in mountain permafrost degradation, but there's very little we know about water in the rock. And the reason for that is that first the process is it's hydrologically very complex, because water are usually from snowmelt, and it's not easy to simulate snowmelt, because snowfall can happen in winter and it only melts in summer, but most of it can sublimate, or also even if it melts, it doesn't mean it will go to the rock, because it depends on the specific hydrology of the snowpack. So it's a very complex system to study. And also getting data and monitoring mountain permafrost is very challenging, because the study sites are very inaccessible, and it's very extreme environment and hard to get there, and steep, as you can see in the picture. And also equipment doesn't last long in these environments. So we think there's some very key, very basic information that we are missing about this process, and we are trying to study. And where we work is it's a place called it's a pillar. It's called Aiguille du Midi, which is, I think it's very famous. It's above the valley of Chamonix, just below the Mont Blanc mountain in the French Alps, and we use it. For us, it's like the perfect natural laboratory. Okay, it's very steep, extreme permafrost. It's 3,800 meters above sea level, so it's very cold. But it's also very accessible. There's a cable car going there with tourists and alpinists going there every day, and so we can easily access it. There's electricity, there's network, and I've just listed here a list of lots of sensors that we are using there. We have boreholes to measure rock temperature profiles, and we have electric resistivity tomography that gives us that can give us information from within the rock. And we use drone surveys to monitor, and time-lapse cameras and snow depth poles to monitor snow depth and accumulation and temperatures, and many things that are listed here. But as I mentioned, it's water that we're interested in. It's all ways around it to get information to put in our numerical models. But again, it's very hard to get hands-on to really go into the water like we saw in the previous presentation. So this brings me to where I'm speaking here. So the Guide du Midi, it's the tunnels carved into the rock where the cable cars are arriving, and the people can go and easily walk to the other side of the pillar. And what it gave us is actually access into the rock and into the fractures. And on the left picture, you see this stainless steel plate that is draining water that are dripping from fractures in the rock. So this was placed a few years ago by the company that runs the place, just so water doesn't drip on the heads of the tourists. And you can see that it on the left here that it drains just to the side. And we just asked them if we can use this system that they built and collect the water and monitor it for our purposes, because it's water directly in the permafrost, in the fractures, exactly what we're interested in. So what we did, we inserted some fluorescent dye in the snowpack that is located exactly above this water collecting system. So you can see on the right picture, there's an upper snow patch and a lower snow patch. And we actually placed two different dye tracers in each snowpack. And I have to say, this happened, the idea came less than a year ago, and we really quickly, with the help of the brilliant engineers that we have here in the lab, we built the system I'm going to show you. So it's really an ongoing process that we're still learning on how to use it. So this is what we've built. So you can look at the central picture. Here is so you see the pipe, we diverted it, the pipe going, and it's going through this siphon that is constantly full with water, and then going down into it's actually a rain gauge to measure the flow rate. And in the siphon is, you can see here on the top left photo, we have the fluorometer that we use to monitor the fluorescence of the water. And also on the bottom right, you can see actually the fracture dripping into these sensors that measure water temperature and also conductivity. And We also, well, there was another room, like a staff room in the Guido Midi that we also knew there was some water dripping and they had some problems with that. So we quickly built this second water collecting system with another fluorometer, but unfortunately it didn't thaw. There was no snowmelt at this location this year. So I don't need to tell you that this year was very unusual with the heat wave that we had. So this was the system. It's actually composed. It's hard to show, but the middle picture and the bottom left, and no, it's the same. But there are two of these boxes because this stainless steel plate is draining in two sides, so we had to place two of these systems. And another thing is we asked the staff that worked there to sample the water for us. So we asked them to do it daily, so we can take it to the lab and examine the fluorescence. And they said, okay, we cannot do it daily, but maybe weekly. And we said, okay, we'll take what we can. And it's actually then we thought about even putting the fluorometer, the sensor, and we were actually very happy we did that because we were getting really nice results. And as I said, it's an ongoing. I was there last week. There was still water dripping, but it's getting cold, so it's probably going to end soon, and then we'll really start processing the data. But I would like to show you. It's my last slide. Some initial results that we have. So the top graph is flow rate of the box that I showed you, and you can see that already in mid-May we had some flow of water, which actually we didn't expect. It was very early this year. And so you can see there's a little peak here and in May 16, and then 3 days later, and a few days later, a few bursts of snowmelt with nothing in between. Also, you can see that it was only in one of the box on the rain gauge. The other one did not measure because they're close together, but it's different fractures. So one fracture had water running, one didn't. And in this red graph, this is one of the sensors that is measuring amino G, which is one of the dye tracers that we put. And you see, whenever there is even little flow, we're getting high peaks of amino G, or it's a signal. And somewhere in mid-June, we started to get regular snow melt, regular flow, with the daily peak and the minimum. Usually it peaks in the afternoon, and in the morning it decreases rapidly. And we see that the peaks in the amino G concentration really follows these high flow events. It doesn't show here, but there's actually a delay between the maximum flow and the peak of the amino G, which is interesting for us. But you can see that at some point the concentration of amino G stopped, reduced, and then completely stopped. But we continued to see flow. Okay, and when the amino G stopped is actually when there was no visible snow on the surface. So we know snow almost completely melted, but we still had water coming. So we know the water it's not a long way, but we're still getting water from somewhere. And interestingly, at some point, also the water on this sensor, the flow really decreased with only occasional, that maybe It could be specific day with rain or snow. And at some point, we actually started getting high rates on the other side. It's another fracture, very late in the season, with water that are not monitored for fluorescence, but we're curious where does this water come from? And again, it's interesting to see that the changes in the fluorescence and the flow are sub-daily. That's why we were very happy that we found TRAQUA and we used the sensors, because if we would have sampled the water once a day or once a week, we would would have missed much of the very important signal that we're getting. And again, the two lower graphs are two other emission sensors for the fluorescent dyes, and we see a completely different signal, which is delayed comparing to the amino G, and it continues even after the snowpack disappeared. So what we think we see is we have other sources of water that are not from this year's snow, and we are very curious about, and I hope maybe next year's webinar I'll be able to show you where they come from. Yeah, so I think that's it for me. I'll be happy to take any questions.
Thank you very much, Matan. So yeah, if there are questions, don't hesitate to ask them in the chat or by raising your hand in the reaction button on top of your screen. There are apparently no questions. I think it's very unusual for people to see
Yes,
dye tracing in the mountains instead of rivers. There's one question from Amaël. How do you interpret those results in terms of risk of instability of the rock?
So it's a good question. These results will be combined with many results. Most of our data goes. We use numerical models. But so it's a question about everything I do, but I think the main thing here would be from these results would be first the timing. We see that the timing of the snowmelt is not exactly when we see water in the fractures, which means that maybe the disappearance of snow would not be a good indicator of water in the fractures. Maybe that's why we see maybe rockfalls later in the season after snowmelt is gone, after the peak snowmelt, because I think maybe we have some storage of ice in fractures. That is obvious. We obviously see it here. It's the first time anyone have ever seen it, as much as I know. So timing of snowmelt, and so obviously timing of risk assessment. I think we see much later in the year that we still might get destabilized by water at least. And I see I'm asked how did we inject the tracer into the snowpack? So well, we had many ideas how to do it. Eventually, we just spill it in the snowpack. It's not big. It's maybe 5 meter or 5 meter snowpack in area. So we just spilled it in a few locations, but we're trying to think for next year how to do it more homogenized in the snow. And I'm happy to hear any ideas people have. It's not easy working. So it's all on a rope. It's steep. It's cold. Without using sprayers, but we think it will just freeze because we have to come in winter. So we're thinking about it. I'm not sure we did it in the best way.
I also have a question. On your last graph, there was the flow that you saw. Is there a way to differentiate between what is the remaining snowmelt and what is new rainfall, for example?
No. No, not with the data we have, not with the information we have. We might. We do have last week I took some temperature sensors from the surface that we put the same day we put the dyes, so we can see if water temperature, if surface temperature will tell us something about if there is snow or isn't snow. But I think maybe for next year we'll just install a camera, a time-lapse camera on the slope, and use that to see if there's snow and how if there's snow during an event, before an event, if there's maybe rainfall. There's not much rainfall there, but it's a good question.
Okay, are there any more questions? Okay, I don't think so. Well, I thank you very much, Matan. So for the participants, don't hesitate to reach out to Matan if you have more ideas about their setup. I think they will be very grateful from the hydrogeology experts.
Yes,
I will share your email in the chat box as well. And thank you for your presentation. The next presentation will be by Amaël. You can stop sharing your presentation, Matan, please.
Hello, everyone.
Hello.
So I'll share my presentation. So good morning, and it's a pleasure to be here today and speak about dye tracing practices with a lot of practitioners from around the world, and I'm sure there will be also very interesting presentation tomorrow. Be sure to catch it. I'm sure we'll learn a lot from each other today. And so for my talk, I wanted to share with you some experience we had on the field with dye tracing in artificial water networks. So it's not so common, but last year we were asked several times to if dye tracing can help to characterize water network, not only on the sense of flow connectivity, but more in the sense of speed, hydrodynamics, and flow behavior. So today I will show you how we managed to bring some, I think, interesting information in those contexts based on dye tracing, and I will especially speak about two study cases in Belgium, and I hope it can echo some of your own experience. So we all know dye tracing in hydrogeology and how it can be a valuable tool for field practitioner. We already had some interesting talk, and the fact is that the use of fluorescent dye combined with in situ field fluorometer is now become a standard. Of course, the field experiment is well designed, and in addition to other reference methodologies such as water sampling and also laboratory analysis. And the point is that the use of field device is quite convenient, together with the fact that they give access to direct information about the results. But what about using dye tracing in artificial network? I mean, channel network, pipe network, sewage system, and even underground facilities like urban hydrogeology, which is a special kind of hydrogeology. Actually, in those contexts, dye tracing is quite common for the detection of hydrological connectivity, the detection of leaks, of misconnection between different parts of the network. And usually the flow behavior, the speed in those systems, the variability of hydrodynamic parameter is not especially targeted by the dye tracing experiment. And I think that the main reason is certainly the cost. I mean, the cost to overcome the challenge to address such questions regarding the benefit of the dye tracing result for a better understanding of the problematic. So about those challenges, what are exactly the challenge related to dye tracing in artificial network? The first is always the same. Is the fluorescent dyes are quickly visible, even at low concentration. So this can be very problematic when your dye has to flow at the surface from the injection point to the sampling point, so not in groundwater. So anybody can see it and be afraid if your communication is not done properly. And so this is the first issue. So you have to have a good detection limit for a sampling solution that is capable to give you reliable results with the lowest quantity of dye that is possible. The second challenge for me is the place you have to monitor, because sampling in natural context and in wells is generally easy, even it is always a field challenge, but here you need to fit with the infrastructure according to the size, the accessibility, the risk of having an in situ monitoring installed in such location. And so the final, the challenge is the spatial resolution. If you only try to answer hydrological connectivity between 2 points, then it is quite easy to have field device or automatic sampler and lab analysis. But when it comes to tackle the flow behavior, the speed, the variability of hydrodynamics along complex networks, then you need to implement a methodology that is capable to have the spatial resolution you need to do it at a reasonable cost. And of course, the sense of reasonable cost depends clearly on your objective, on the value of your information. So this is the cost you can afford, and it has to be related to the benefit of your information. And so you need to be able to get a high resolution information without spending too much money, which is quite difficult. And for me, this last challenge is the real challenge for using dye tracing in artificial networks, because we have to build a methodology and a monitoring system that gives you the opportunity to add a valuable information about the hydrological behavior, but without building a methodology that is too expensive regarding the benefit that it can bring to the question, bring to the research. And in that sense, compared to natural groundwater that are difficult to access and where dye tracing can be a good asset, even at higher cost, this is not necessarily the case in surface water and in artificial network. So it's not the first option, I mean. So let me present you two study cases that we've done this year with TRAQUA, and where dye tracing was a valuable asset in the characterization of artificial networks, and where we managed to overcome the issues I mentioned just now. First of all, this is a high resolution dye tracing in an artificial network in north of Belgium, and then an example of dye tracing in sewage system, just to better emphasize the challenge related to dye tracing in sewage system. And so both of those studies were done with TRAQUA stream fluorometer, since we developed and built this tool since a few years now. And so next to the scientific challenge that is related to those contexts, we also had a technical challenge to see how our instruments can be implemented on the field in those contexts, how they perform, how they or not, how they not perform, and how they ease or enable the realization of such experiments. And so how we can learn for future studies and have implementation of modification, improvements in the probes. So every field case is very different in terms of typology of the place, the installation, the water quality, the objective, the risk. And so we were also interested in this approach to see if the tool can be an asset or not. So the first study case I want to show you is in North Belgium, near the Belgian coastline. It's a region called the Weskuspolder. And this is a region that suffered from a severe drought in the recent year, where the water production is really a challenge. Groundwater is not suitable for consumption, so the water producers use surface water to be able to provide drinkable water to the population. And so they take water in surface channels that were built, as you can see on the right pictures, built to drain the fields and enable the agriculture in this area. And since we are close to the sea, the gradient is very low and the direction of flow is strongly dependent to a local condition of inflow, there is temporary dams, sloughs that modify the water level. And so classical methods to evaluate the hydrodynamics are difficult to implement in such a context because there is a very low flow velocity, low gradients, and the size is large, a few kilometers for the channel network. However, the water producer here was interested to know how water is flowing in this channel, in which direction, at what speed, and if the hydrogeological behavior is changing along the supposed pathway of the water. So in coordination with local farmers, we install 12 field fluorometers along the supposed pathway of the water flow. And the water producer was especially interested to precise the water flow behavior from point to point at a local scale. Because the supposed pathway of water flow was not certain, and he wanted to identify potential diversion in the water flow in the system. So as you can see on the left, the fluorometer was installed in black PVC pipes to avoid daylight influence and to ensure a stable and safe location, because we wanted to repeat the operation. In total, we made 3 dye injections with sodium fluorescein and with the same field configuration. We had different gradients and discharge conditions to test the same dye tracing procedure. So we set up the probe with a 5-minute time step for sodium fluorescein, so the dye, also turbidity and temperature. So we can both follow the dye behavior and also the natural conditions with turbidity and temperature, which are important to detect potential artifacts in the dye restitutions. So this network was left for 2 weeks for the 3 tests, and each test lasts for 3 or 4 days for the 5 kilometers long pathway here. And so the interest was also to see if such a system can be easily implemented on the field, because obviously here, this is what cost most of the budget for the final clients. So the time that is needed to install the probe. Here, it takes about half a day, so 4 hours for the installation. So the costs was quite limited, and the cost of the information that will be given at the end with the dye tracing was in good agreement with the benefit it will bring to the water producer. Of course, the field environment here was not very complicated. This is not like Matan showed us just now, but it showed that for such an application, dye tracing can help. So here we have some results we've got for one of the dye tracing for the dye tracing experiments. So we have nice breakthrough curve for the different place I just show you. And we have a nice succession of breakthrough curve from point to point. And that enables us the calculation of flow speed, maximum speed, modal speed, and the average dispersion along each portion of the system. That part of the analysis was made by the water producer and hydrological engineers. But at first, we can evaluate that the speed of flow is decreasing as we move downstream due to the decreasing of gradients, and also the longitudinal dispersion is decreasing for the last portion of the system. Here it is the final graph with all combined breakthrough curves, where you can see the progressive dilution along the pathway. Of course, the starting at 0.7 is not even visible because the concentration is quite low. And so those results enable the water producers to feed its hydrological model for the flow and transport in the channel network that is used at the end for water abstraction. And since we repeated the experiment for different gradients and discharge condition, it also helps to optimize and to adjust the management of this artificial system based on a quite simple setup and rather a quick experimentation. So what we did learn from this study case? First, we learned that we managed to use dye tracing with a high spatial resolution to bring a quantitative information about how this system works at a cost that is in accordance with the cost/benefits exigence of the water producer. Clearly, here a lower spatial resolution and a lower temporal resolution for the data will not be able to have add a significant information in terms of speed, in terms of dispersion change, and that would be valuable for the water producer. But also here in that situation, using water samplers and lab analysis for the 12 points, considering the transport, the handling, the lab analysis will not be would be inappropriate in terms of cost and will not add a significant information. And finally, for injection 1 to injection 3, we adjust the quantity of the dye, consider to have a valuable signal at the end without injecting too much dye. And this is also an asset, I think, of such an installation, because we were able to repeat the operation very easily at a very low cost, since the monitoring was in place. So we are able to start with a very low quantity of dye. First, quickly check if it is enough to have the final data and final information, and then adjust in consequence to lower the impact we have on the media. So second study case about dye tracing in sewage system. We were involved in a project in a sewage system of Pevenster, which is in eastern Belgium. This region was highly impacted by major floods during last summer in 2021. Nearly 40 people lost their life in this event in Belgium, and the region was really devastated. And it's in this area, quite commonly, the sewage system is built along the rivers. And since this event, a lot of the sewage pipes were damaged, and the most problematic issue was the loss of the wastewater treatment plants that were damaged by the flood. And so, since more than 1 year, the wastewater of 150,000 people is now flowing directly in natural rivers without any treatment. And so to tackle this issue, the wastewater has to be treated inside the sewage system directly. This is done by another Belgian company. And for this specific application, they need to have a precise characterization of the network status. So identification of leaks, of connectivity, hydrodynamic at a local scale, speed of the water. Local scale mean a few kilometers between a few villages in a suburban area. So we used fluorescent dyes, which is not very often used in sewage system, with the objective to characterize the flow at a local scale in small sewage pipe in a dense suburban network. But of course, there was some technical limitation for the implementation of dye tracing in such a context. First of all, most of our access were on the street, on sewer holes, so you cannot let those holes open for days, even for hours, because the traffic is running at the surface in the street. So you definitely need to hide yourself and your equipment inside the sewage system. As I already mentioned, this is small systems in village and small towns, so the size is limited. And the access is not very easy. The flow is not important in such a system. So again, here we need to adapt ourselves to the situation, being able to sample in such a system. And the last limitation was the suspended solid content, which is high and especially smelly. So you need to have something that will avoid absolutely obstructions of the sewage system and all the boats that are carried in the water. So we take advantage of our standalone fluorometer that are fully submersible, and so we don't have a data logger next to it. We just immerse a probe in the wastewater, of course, properly fix it, but with a limited impact on the water flow. And so it allows us to install something that is not visible at the surface, quickly installed, quickly removed, so we can perform multiple dye tracing in the area from point to point and also from one point to multiple different points downstreams. One important access here was the sanitary exigence regarding the work in such an environment. This was beginning of this year. The COVID highlighted this because for this particular application, due to the COVID-19 pandemic, it was especially difficult to sample water in the sewage system, basically regarding the regulation. The potential impact on health force was important. So in terms of insurance, it was an excluding case, and so potentially problematic for our company. So actually the issue is the same, whether there is COVID or any other disease that is carried by such a sewage system. So it can be harmful for the practitioner, and having an in situ instrument with a limited contact with the water was clearly a benediction here. And I would add that sampling the water in a context of COVID-19 would be a nightmare here, because the sampling, the transport or even the analysis of such a water do need special procedures. So it would add a lot of complication and so a lot of costs for the final clients. So the in-situ solution was safe for the practitioners, and it offers a lot of benefits both for the client and for us as a field practitioners. So a few results. Just to illustrate what was done, we made 4 dye tracings for this project. We recorded the dye, sodium fluorescein, the turbidity, the temperature. Turbidity was used to have an information of the suspended solid in the water wastewater system that could impact the quality of the results. And so a few conclusions about this second study case. Clearly, we learned that dye tracing in sewage system can be easily made with an in-situ probe that enables the sampling in small, difficult to access conduits with a limited impact on the flow. Also, it was nice to have something that prevents COVID, but also any other disease issues due to the specific environment. It gives us a tool to quickly investigate the flow behavior in terms of flow speed and to enable the in-situ treatment of the wastewater in that case, because there was no wastewater treatment plant. And again, here, in addition to the health issue, the water sampling was not possible because of the size of the network, the access, and of course also because of the sample precaution we need to take. So also we were we had direct results that enable us to adapt the future injection in real time, because we had no budget to go on the field several times, so the cost was limited, of course, and so we take advantage to have direct results to be able to adapt or future dye injections to make a lot of dye tracing during one day. So let's move to some conclusion. So the question we asked was, how can dye tracing add valuable information in artificial network characterization? By valuable, we mean information that is really a benefit for the client, given the cost of the technique. Our objective behind the science and behind the specific problematic of the application was to evaluate how dye tracing methodology can really benefit in such application in terms of the quality of the information they give versus the effort and the cost of implementation that is needed. And we observed that the ability to obtain a high spatial resolution is the first key to meet this objective, because what is clearly needed for artificial networks and surface hydrology is something that enable detailed data about the flow behavior that is not necessarily accessible with alternative methodology. So here we found that we need a high number of sampling points at a reasonable cost. So a reasonable time of implementation on the field, reasonable time for maintenance, and the ability to fit with variable sampling environment. This is the first key for us. And the second key we found is the ability to work invisibly and to repeat the operation. If you have an automatic network of in-situ measurement with a high detection limit, and a precise detection limit, and that ensure the use of low quantity of dye, then you can work with trial and error procedures and adjust your methodology at low cost and easily collect a lot of valuable data for different hydrological condition or different condition in the system. So some words to finish my talk. I would like to thanks all participants to take this time this morning to attend this meeting, which is certainly not finished because we have also presentation tomorrow. And I would like to thanks also the other speakers that take their time to share with us their experience in dye tracing. And finally, would like to thanks Sophie that organized this webinar. I'm sure we'll find future opportunities to share, to have all other webinar like this in the future. So I will take any questions, and I thank you for your attention.
Thank you, Amaël. There are already some questions. So one is from Romsa Fauzan. I'm not sure if it's a question for you or rather for the first presenter, Romain. So how to know the advection dispersion from tracer test data?
Yes, I don't know if it is for Romain. You can apply a lot of different kind of models to fit artificial breakthrough curves to your field data, and to evaluate hydrodynamic parameters such as parameters and coefficient for advection and dispersion, to fit, for example, the longitudinal dispersion, porosity to your field data. But I don't know if this question was linked with the presentation of Romain or mine. This is something what we didn't do for the first study site I showed. Let's say just give the data to the final client.
Thank you. A second question from Melanie Huaman. She asked, the algae that are generated in the sewers, can they damage the fluorometer, and can this cause an error in fluorescence reading?
Of course. Here, for this example, this was very quick, so we didn't have a lot of trouble in terms of hardware. I mean, the biofouling or something like that. But definitely it can be an issue if you let the instruments on the site for weeks, especially in such a high water content conditions, and it can cause error in the fluorescence reading. That's why here we also measure all the channels to evaluate the variability of natural fluorescence, not only the channel for sodium fluorescein, and also the turbidity that give us an idea of how the suspended matter contents is evolving in the system, because here for the system there was a lot of during most of the time the water was quite clear, and you have just some period, some spot in your monitoring where there is a lot of turbidity and of suspended matters, and so this is clearly showed by the turbidity monitoring, that so we can interpret your dye tracing result in accordance.
Thank you. Another question from Carla Perez Esteves. She asked for the case study 1. Would it be possible to measure also horizontally the flow velocity of the canal? And can we also use it for monitoring groundwater in piezometers?
To answer the first question, yes, that's exactly what was done in this study case. The main interest of the water producer was to evaluate the horizontal flow velocity in the canal, in the channel. And that's why we calculate the flow velocity at each point. Of course, it's an average velocity from all the upstream sections, but with a precise analysis, you may calculate the flow velocity for each of the section. That's not something we done at TRAQUA, but definitely that was the interest here. And I'm not sure to understand the question. Can we also use it for monitoring groundwater piezometer? You mean the probe that we use, the fluorometer? Yes, that's also something which we done. Here we install those probes in PVC pipes just to have a fixed spot, because we came back on the field several times, so we needed something that is convenient to insert the probe into the PVC pipes and then remove it, so it is always at the same place and it's safe. But definitely when we use it in piezometer, of course you need a diameter of the piezometer which is enough to be able to insert the probe inside it, but that's the spirit of those fluorometers, to be able to be installed in the piezometer at the depth you want, or even install different fluorometers, one above each other in the same piezometer. That's also something we have done, but not related here to artificial network. That's why I didn't show this here.
She also has another question about the diver inside the PVC pipe. I guess it's related to the flow velocity of the horizontal flow measurement.
I guess it was related to the use of the probe inside a piezometer, where you install also diver.
Okay, I think you have answered her questions. Are there any other questions? In any case, I will share Amaël's email address here. So if you have additional questions, don't hesitate to contact him. Voilà. So this was the final speaker for today. Unfortunately, we had another speaker planned, but he was disposed. Of course, you are more than welcome tomorrow. I hope to see you all for the second part of the webinar. So tomorrow from 3 to 5 p.m. Central European time or Brussels time. Normally you have all received the link via email, and thank you all for your attention. And as mentioned at the start of this webinar, the webinar is recorded and will be shared after the webinar series somewhere probably earlier next week. So thank you very much and have a nice start of the day.
Thank you very much.
You. Bye.
Thanks.
Thank you. Bye-bye.